Hello everyone, how's it going? In this video, we're going to see how we can remove the distortion caused by the camera lens. So if you look into these images, especially notice the edges of these images, they look like they're stretched out or they're blurry over towards the edges. So this is caused because of the lens of the camera, and the lens of the camera is in a circular fashion. Since it's a spherical lens, it causes this distortion, but the image that you're looking, that's a rectangular image. So the spherical image that was captured by the camera, it is being stretched out and then represented us in a rectangular fashion. And that's the distortion caused because of the camera, the type of camera you're using. And different cameras cause different types of distortion. It doesn't mean that the distortion that we are seeing in this camera or this particular video will be the same in every camera. So it depends on the type of camera you're using and what kind of recording you're doing. So every camera is different. Now let's see how we can fix that and how we can interpret it. So in our previous section, we saw that OpenCV has an inbuilt command, which is where if you call the find chessboard corners function, it can detect the corners, and then using the draw chessboard corners, it can also draw the corners for us. So OpenCV already has this inbuilt function. So if you just tell OpenCV that I have this image of a chessboard, which is expected to have about so many number of horizontal boxes, in this case 1 2 3 4 5 6 7 8, so 8 horizontal boxes and the same number of boxes on the vertical direction as well. So 1 2 3 4 5 6 7 8. So it has 8 boxes on the horizontal, 8 boxes on the vertical. And if you just let the find chessboard corners, that these are the number of corners, we have put down 7 and 7 just because index starts with a 0. So even though it's 8 by 8, you're just saying that it's 7 by 7 boxes. So then it goes into the find chessboard corners and identifies the corners. It can also tell us what's the distance between these corners horizontally and vertically. So how we can use this information to remove the distortion caused by the image. So let's look into that. Now, for this purpose, we want to do something called as calibration. So we are just letting the function know, letting the program know that the image coming from the camera is distorted by so and so amount. And in order for you to interpret the real image, you want to nullify this distortion. So for that purpose, we want to understand what that distortion is. So normally what you would do is, how to go about doing this is, you take your same camera which you're using to record the video of the path, or using that video for the self-driving purpose. That same camera, you want to go and take a picture of a chessboard and take multiple pictures of the chessboard from different angles. So you can see this particular repository called the advanced lane lines from this gentleman. He has taken up about 20 images, and that's the ideal number, about 20 images of the distorted or of the chessboard with that same camera that you're going to be using. And this distortion, all these images are going to be fed to this algorithm, where it will go through all these images and try to understand how much this camera is distorting an image. Once we know that, we can just nullify that effect and then give us the undistorted image for us. So enough of talking, let's see how we can do this. Now, we are going to be using this particular repository and all the images that are being used in this particular repository. For our purpose, if you're doing it in real time, it is better to take real pictures of chessboard with our own camera, the same camera that we're going to be using for self-driving purpose. But for the scope of this course, we're going to be relying on this repository. So I'll link into the description so you know where you're copying it from. So just copy this thing here, just copy the link of this repository and come down here. Now, this is the same Collab Notebook that we have been using all along this course, but I've opened it as a fresh notebook. What I mean by that is if you go into runtime and just do factory reset runtime, it'll open up as a new Collab. You'll still retain all the codes from the past, but it will open up as a new directory because we want this in as an empty directory. So right now it's an empty directory. It only has the sample data folder that comes in default with any Collab notebook, but all our files and all our settings have been removed. So let's go back and restart doing things here. And the first thing you want to do is understand where are we in this Collab. So if we just say list ls, it shows that it's in the main directory where the sample data folder is also available right here. And while we are here, let's clone the repository. So we already copied the link to this Collab from here, or to this GitHub repository from here by just clicking on this. And now we're coming here and we just say git clone and we paste this link here. And if we just run this, it opens up, or it's downloading all or cloning all the repository, all the items from this particular GitHub repository. So it looks like it's done. And if we open up here, it's advanced lane lines. Now let's open up this folder in our command line. So we're coming here, we say change directory, which is cd. And if we cd and we want to open the advanced lane lines folder. So click on this, and now the cursor or the power is inside the advanced lane lines folder. So we are in this particular thing. Here we are particularly interested in this camera calibration folder, where it has about 20 images of the cameras, of the video, of all the images of the chessboard that was taken up, and we're going to be using that. So let's close this back again. Now, the idea behind this project is to understand the distortion, right? Now, one way of doing that is using the find chessboard corners, using the draw chessboard corners. OpenCV can help us identify where these corners are available in the image space. Image space is where how the image has come out from the camera, the distorted image. So OpenCV can tell us where the corners are available in the distorted image using the find chessboard corners. But we know that a chessboard is a symmetrical image, and it has all these boxes which are equally spaced. So we'll rely on that equally spaced notion and say that, okay, in reality, these chessboard corners are supposed to be equally spaced. And I'm going to compare these equally spaced corners to the corners that my OpenCV find chessboard corners found out for me. So the image space and the real space. For the real space, we'll call it as object space. So what we're trying to do is find the relation between the corners that were detected by OpenCV's find chessboard corners and the corners that should have actually been in place for that particular image. So with that, we will just combine both of them and try to identify how much are these corners deflecting from their points because of the distortion in the image. It'll make more sense when we start doing it. So, but that's the gist of it. We're trying to compare how much are the corners displaced in the image versus the corners that should have been in real life or in real space. They should have been equally spaced from each other. So using that synonym, we'll try to understand how much distortion the camera is causing on our images. So let's open up this new command here, and we will import all the libraries that we need. So first thing we need is name numpy as np, because we are going to be using a lot of matrices, especially the object matrix, where we are assuming that our chessboard is supposed to have so many corners of so many or symmetrical distance. For that purpose, we will be using numpy especially. We are also going to be using cv2 OpenCV, and we are opening, we need another function called as glob, and I'll show you why glob is being utilized here. The purpose of glob is basically to read all these images in one go. So it will go through the whole folder and take out all the files that look like a JPG and then read it for us. Now, once we have all of this, now we're going to be initializing what is called as the object points and image points. Object points are nothing but the points or the location of the corners in the real life where they should have been equally spaced, and image points are the points of the corners obtained by the OpenCV's find chessboard corners. So all these corners that are being detected by OpenCV, these are nothing but image points which are identified from an image. But object points are points that we are going to be assuming that since this is a chessboard and it's of equal distance, these corners are going to be equally spaced in so and so region in real life. So right now we are just initializing them as empty arrays, but as we go about in the program, we will then fill all these corners or all these points with actual numbers of the location of the corners. So let's start by reading all the images. So we have all of these images inside the advanced lanes line folders and inside the camera calibration folder. So let's first of all read all of these 20 images. And for that purpose, we will use this glob function. This is an interesting function which helps us read everything in a given directory of the format that you want. So if you say, okay, I need to read everything in this directory and please read and give me all the file names, or if I want just to find the JPEG files or just the MP4 files in this folder, it can filter through the directory and just pull up all the files of the extension that you're interested in. In our purpose, we know that the camera calibration folder is nothing but JPEG files or image files, and we will just read everything. So we call glob.glob, and this glob function, we are just saying that everything in that folder, please go ahead and read it. So we're just initializing the location. We're saying, okay, please read everything. This star here, it means that you're asking glob to read everything. And the format is nothing but showing which folder or which directory we are going to be reading. And in our case, it's the camera calib. So we say camera underscore calibration or CAL, and we're just letting glob read all the images for us. And if we just do print images, it should read all the images for us. So if we run this, we can see that it's reading all the images here, and it has printed them one by one here for us. So it's nothing but an array of all the image files with the names in this particular variable called images. So let's start by reading all these images and see how we can initialize this. So all these images are nothing but the chessboard images, and we will be using the find chessboard corners function in OpenCV to identify the corners of these image points. And before we go that, let's initialize the object points. So these object points are nothing but the location of the location of the chessboard in real life. So we'll initialize where the location of the actual function should be available. So for that purpose, let's create a zero matrix of 3 by 3 where we are saying that the x coordinate, y coordinate, and the z coordinate in the real life of the chessboard is 0, 0, 0. And let's initialize that. So we say objp equal to numpy zeros. So numpy has this function and it's zeros. And here you want to specify the matrix to have so and so number of rows and so number of columns. So in this particular calibration image, this image has 10 by 7 boxes or 10 by 7 corners. Let me open up a clearer image that might be easier for us to pull up. Okay, yeah, so this should be helpful. So if you look into this image, it has about 10 boxes on the horizontal direction. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it has 7 boxes on the vertical direction. So if we count 1, 2, 3, 4, 5, 6, and 7. So it has 7 boxes on the vertical and 10 boxes on the horizontal direction. So let's use that information, and we say let's open up a zeros matrix, which is going to be having 9 by 6, because you're indexing it from 0. So instead of 10 you're putting 9, instead of 7 you're putting it as 6. So you want to specify a 9 by 6 matrix, and with 3. So 3 is nothing but the x, y, and z. So you're initializing the three channels for the object points, and we are saying that it's a floating variable or floating integer of size 32. So it's a floating point of size 32, and we want to close this bracket and another bracket from here. So once we have all of this defined, now we want to convert this particular object point, which is in real space, in a 3D function, because we initialized it with a 3-dimensional with the z coordinate. We want to, since we are going to be comparing the image points from the fine chessboard corners, it's getting a little bit confusing at this point, but stay with me, and I'll try to make it as simple as possible. So if you try to understand, this object points is in real space, and it is being defined by the x, y, and z coordinate. And the image point that we are going to be identifying using the fine chessboard corners, and I'm referring back to this image, these image points or these corners in the image, this is in a 2D space, so it doesn't have the z coordinate. It only has the x and y coordinate. So now what we want to do is translate our x, y, z coordinate plane, so all the 3-dimensional plane, into a 2-dimensional plane. And for that purpose, NumPy has a function called where it can translate a 1-dimensional matrix into another dimensional matrix, or a 3-dimensional matrix into a 2-dimensional matrix. And let's see how we can do that. So we are initializing OBGP, and we are saying that it's an array which is now supposed to have only 2 dimensions. So we're saying it only supposed to have 2 dimensions, and we are creating a mesh grid. So it's called NP mgrid, and this mesh grid is nothing but creating a grid for us of the values that we initialized with. So we have all the zeros here, and that's the size of the matrix. And now we are creating a mesh grid, and this grid will use the values that we provide. And since we know that our matrix or our range of our boxes are from 1 to 10 or 0 to 9 horizontally, and 1 to 7 or 0 to 6 vertically. So we are telling a mesh grid, we are telling NumPy to please create a mesh grid for us on this OBGP array, and this mesh grid is supposed to have 0 to 9 and 0 to 6 boxes of so and so values. So the first box will be 0 by 0, the second box will be 0, 1 horizontally, and vertically 1, 0. So you're now creating a mesh, and you're trying to understand that this is how my mesh is created. It should be a square bracket because it's nothing but an array. So mesh grid is created. Now this mesh grid is created in a 3-dimensional space because we initialized the third variable, the third Cartesian coordinate, the z coordinate. So for that purpose, we want to remove the third coordinate, and we will first transpose the image or transpose the matrix by writing the T. So this T will nothing but transpose this matrix and then reshape the matrix into a 2-dimensional image. So we say it's going to be a 2-dimensional image. But what happens is when you're trying to convert an image of 1 dimension to an image of another dimension, then you need to account for the other information that is available. And for that purpose, what happens is you're just nothing but changing a matrix. So a matrix which had one row or two columns now will have one row and maybe 6 columns. So it changes the image because you're trying to change or trying to convert one image of one dimension to another image of another dimension. So for that purpose, we don't know what that other dimension is going to be because we are converting it from a 3D image to a 2D image. So we just say NumPy, hey NumPy, I don't know what the image is. I'm sorry about that. I don't know what the new dimension is going to be, but you are free to identify whatever dimension it is and make the image the way you feel fit. So we are giving open flexibility for NumPy to calculate the new dimension and then give it over to us. So for that purpose, we say -1. So -1 is nothing but giving flexibility for NumPy to change the image into whatever format we want. And that's all the complex function we are going. That's all the complexity that we have for today. Once we understand this, everything else is going to be easy for us. Let me go back and explain what we're doing again. The purpose of this whole section is to create an object space or a 3-dimensional space of the real life chessboard. So we are assuming that there is a chessboard in real life which is of X dimension, Y dimension, and Z dimension away from the camera. So we have this information about the chessboard in our mind. It's not in reality, it's in mind, and that information is important for us because in real life we know that the chessboard is a symmetrical image. It's a symmetrical object which has a set number of horizontal width and a set number of vertical width, and it's a square grid. So all the images, all the boxes are of equal length in reality. That's the assumption that we're going with, and we are converting that assumption that we have about this 3D image into a 2D image using the mesh grid and transpose function, reshaping it into a 2-dimensional image. So from a 3-dimensional matrix that we had originally, we are converting that into a 2-dimensional matrix using the reshape function, and we are giving -1 because once we convert an image from a 3-dimensional matrix to a 2-dimensional matrix, the number of rows or the number of columns affect, and we're telling NumPy you have the flexibility of converting it into the format that you want. All I am interested in is the X and Y plane. So I'm only interested in the X and Y. You take care of the rest and make sure that I'm getting an image or a 2-dimensional matrix out of my 3-dimensional space. So that's all creating the object matrix for us. Now what we're going to be doing is going through each and every image in this glob variable, all these 20 images in that calibration format, and then using the find chessboard corners function that we saw earlier to identify the corners of the 2D image or the image points, and then compare it with this OBJ points that we calculated here. So let's go through that. We'll go through each image. So we say for image in images, let's read through all the image. We say img equal to cv2 imread image. Because image is holding the file names of all the images, it will just simply read the images for us. Now the grayscale image, we're converting it into a grayscale image because the find chessboard corners work better in that way, because it's easier for it to understand the black and white nature in a grayscale image. So we say cv2 convert color, and we're converting the image img image into a grayscale image. So we say cv2, let me move my cursor here, cv2 color bgr to gray. So we're just converting the color from BGR to gray. The third option is for us to find the chessboard corners. So we will go back to the same function here that we had, the find chessboard corners, which uses the gray image, the number of corners, the number of X corners and the Y corners, and the none flag. So this same function will come down here and use it. And we say we initialize the return flag, and we call this variable called corners. This corners is going to save all the corners of the image points, and find chess board corners, not the SB version, but the corners, just the plain corners. And we are specifying the gray image that we have and the 9x6 corners that we have. So we say 9x6. So this is how it does, and you're initializing the none flag. To make it easier, if we can even remove the gray image, and we can also try running it on the regular image, but it's okay to run it on an irregular image as well. So let's do this. You can test it out with both gray and color, and find chessboard corners will do the job for us. Now we initialize a flag called if return flag. If the return flag is true, which means that it has detected the corners, then go through and append our image points. So fill up the image points and the object points. Come here, img points dot append corners. All the corners will go through, and obg points append the OBGP that we initialized right here. So once we have all of this information saved in our object points and image points, so this is just showing us that where the corners are present. So these image points or the IMG points, they store information about where the corners are present in the 2D image, the distorted image, and the OBG points have information of where the corners should be in real life without any kind of distortion. So now it's only a matter of comparing these 2 points and see how much of these points are varying from each other. And for that, OpenCV has an inbuilt function called calibration, and we'll look into that right now. So come back here and we write down, or let's identify the shape of the image that we have. The shape is equal to img dot shape 1, which is the height, and img dot shape the width. So we're just initializing a variable called shape. This shape is nothing but the information about the height and the width of the actual image that we are now going to be testing. Now OpenCV has this function called calibrate camera. So let me show you CV2 calibrate camera, or it's a small caps lock. Yeah, so calibrate camera. So this calibrate camera, this function is able to take information about the object points, the image points, the size, and then initialize all these cameras and the camera information, the matrix and the distance coefficient, or the distortion coefficient. So what it does is it takes all this information about object points, image points, the size. All this information are not so important. If we have them, that'll be wonderful. But if we don't, it can just run with these 3 information, which is the object points, the image points, and the size of the actual image. So if we just give these 3 values, it'll give us the return flag, the camera matrix, and this is the most important function, the camera matrix, the distortion coefficient, and the R vectors and the T vectors. So this is nothing but the information about the camera, of how much it's distorting the image, which we are not so much interested. We are only interested in this camera matrix and the distortion coefficient. So this camera matrix and the distortion coefficient is is nothing but calculating the property of the camera, of how much it is distorting an image. So as long as we know this camera matrix and a distortion coefficient of our camera, we can use this information to undistort any image. So let's go about doing that. And we saw that it is giving us about 4 or 5 values. One is the return flag, the matrix, the camera matrix, and the distortion coefficient, we'll call it as dist, and the R vectors, which we are not interested in, the T vectors, which we are also not interested in. So we just initialize it as underscores. Now we are taking the calibrate camera function, and we're giving the OBG points that we initialized up earlier. And we are also giving the image points that we initialized up here already. And we're giving the shape of the matrix. We are not providing the camera matrix and the distortion coefficient because we don't know that. But please, we are requesting OpenCV to calculate that for us. So once we have the matrix, the camera matrix and the distortion coefficient, now we can undistort any image what we need. And for that function, for that purpose, we will now create or call a function, initialize a function that we can now, once we know the matrix and distortion coefficient, now we can create a function where if we call this function, it will just use the matrix and this distortion coefficient and calculate or give us the undistorted image for us. So we say define a function called undistort, and this undistort function will take a distorted image and return a undistorted image. And for that, OpenCV has an undistorted function called undistort. This undistort is nothing but using the information that we calculated with the matrix and the distortion coefficient and give us the undistorted image. So we say distorted image, use the undistorted or use the distorted image, use the matrix that we initialized earlier. We also use the distortion coefficient from earlier, not because I don't have the distortion or the thing, and so I'm just saying none. And it's asking for the new camera matrix. The new camera matrix is the same as the old camera matrix. I don't have any kind of new distortion matrix, and I'm just affecting, or I'm just working on this new, on the same camera. So it's the same matrix, and it just returns the distorted image for us. So if we go about running this, hopefully it does not give us any errors, but it did, and it's telling us that we have an issue in the float variable. Let's see, let's go back here. So it looks like we have created a couple of brackets. So yeah, we have too many brackets open up here. So we close one of the brackets, and let's rerun this and see if this causes any issues. So it looks like it's going through the images and creating the matrix for us, and it's going to take a few seconds. And once it's done, it looks like it took about 10 seconds, and it's done reading through all the images. Perfect. Now let's go through one of these images and try to see if how much is it actually undistorting, and how we can use this undistort function for our purpose. So we made the backend. We calculated the matrix, and we have a function ready for us. So if we give a distorted image, it will give us an undistorted image back to us. So let's see how we can do this. We initialize a variable or initialize a image called cv2 imRead, and let's read one of these images that we have, the camera calibration image, or the camera. Let's read the calibration 1.jpg. So we'll say imRead, and this image is present in our camera calibration folder, and the image file name is calibration1.jpg. And please calculate the undistorted image for us. We say undistort img. So it will give us an output image which is undistorted. Very good. Now what we do is let's display this image in our browser so we can see what kind of undistortion it is doing. So we say from Google Colab dot patches import cv2 underscore im show. And once we have this, let's just display the image, the original image and the output image, which is the undistorted image. So let's display it here right in the browser. So you can see that this is the original image. There is some curvature here. I don't know if it's clearly visible, but if you go down and look into the other image, the curvature has gone away. But what we can do is try to put both of these images side by side. So I'll initialize a function called display and use our numpy to create a horizontal stack. So horizontal stack or hedge stack. So it can take our two images, the img image and the output image, and create a horizontal stack of both of them. And we can use this display to display both of them side by side to each other. Let me comment on both of these so we are not confused. So let's now rerun this, and now we can see both of these images are placed side by side, and this particular boundary here is nothing but the effect. So you can see that this particular region right here, it has some sort of a curvature present, and this curvature is nothing but the distortion. And if you look into this particular image, which is right starting from this boundary to this boundary, you can see that the curvature has gone away, and this image has nothing but it is now stretched out or made in a straight fashion. So you can see how it's undistorted, where all these corners now seem like they are in a straight line, whereas here you will see that it has almost like a bulge, which is going out more, straightens out more in the center. But as we move towards the edges of the image, there is a bulge where these images look like they're skewed, and there is a bulge right on the edges as well. So this distortion is removed by the undistort function. We can see that all of these chessboard corners look like they're in a straight line. So that's what the undistortion function is doing for us. So at this point, we just understood how we could calibrate the image. Now let's see what we can do in the next stages.